Yeah. Good afternoon, everyone. Today I'm here as your teaching assistant for organometallic chemistry, instructed by Professor Debabrata Maiti at Department of Chemistry, IIT Bombay. And I am doing currently a PhD from Department of Polymer and Process Engineering, supervised by Professor Pradeep Kumar Maji and Professor Kaushik Ghosh. Today we will be dealing with assignment number 2 of year 23 and assignment number 4 of year 22. Before starting, I shall tell you that we will discuss about the problem introduction and my introduction solution of the assignment 2 for year 23 and 4 for year 22 and basics involving in it. Oh, my name is Shiva Singh and I have started my PhD from IIT Roorkee Saharanpur campus and I am working on cellulose chemistry. And my master's was awarded from VNIT Nagpur in chemistry and I have did my graduation honors from Delhi University in chemistry, and my higher secondary and secondary educations were done through State Board of Uttar Pradesh. During my PhD tenure, I have published around nine uh, research articles, three book chapters. I have also got three awards: Prime Minister's Fellowship, Inspire Fellowship, and Assemble Scholar. I have also attended around 10 book chapters. Sorry, around 10. Just a minute. Hello. Okay. Yeah. Sorry. Let's start again. Yeah. So I have completed my introduction now. Let's move to the assignment number one. Assignment number two of year 23. In the following hydroformylation reaction, which of the are correct? Which of the options are correct? It is alkene reacted in the presence of hydrogen and carbonyl with the cobalt complex. So we have four options: forms acyl intermediate, forms an adduct with olefin reactant, reacts with hydrogen, eliminates propane. So what may be the correct answer for this question? You have 2 minutes to solve this question. Then I will be introducing the catalytic cycle of this reaction. The question is, in the following hydroformylation reaction, which of the options are correct? Alkene reacted in the presence of hydrogen carbonyl with the catalyst of cobalt and resulted in a carbonyl compound. We have option: forms an acyl intermediate, forms an adduct with olefin reactant, reacts with hydrogen and eliminates the propane. Do we have a correct option here? Do we have a correct option? Okay, let's move to the solution. So if we see here, this is the catalytic cycle. This catalyst follows, and here is our alkene. Suppose R is our hydrogen group, as given in the question. Sorry, R is our methyl group. So, firstly, this methyl comes and interacts with the cobalt complex, and this follows in a parallel pathway. Then the formation of this complex and carbonyl introduction, and here we can see this forms an acyl intermediate. This is the intermediate, and then hydrogen comes, and the elimination occurs, product formation, and again the catalytic cycle goes on. This is the way the question should be addressed. Let's move to the next question. The bond angle for titania carbon-carbon in crystal structure of following complex is severely distorted. What may be the reason? If we see here, the bond angle is coming around 860 degree. Why this bond angle is very distorted? The answers we are provided here are hydrogen bonding, agostic interaction, steric bulk of phosphine ligand, higher formal charge on metal. So such type of questions I have already addressed in my previous lectures for metal mediated synthesis, but we will discuss it again and I will give you the reference. Also, I have provided the reference for this question also. You can directly go and follow this research article for this particular question. Here again, the bond angle for titania carbon-carbon in crystal structure of the following complex is severely distorted. What may be the reason? Hydrogen bonding interaction, agostic interaction, steric bulk of the phosphine ligand, higher formal charge on the metal. What may be the answer for this? The bond angle for titania carbon-carbon crystal structure in the following complex is severely distorted due to the agostic interaction. Sorry, due to the agostic interaction. I will tell you how. This is our complex here. If we see this type of complex, here this hydrogen is directly interacting with titania due to the low valent deficiency of electron. It is pulling the electrons of this particular group, which results the distortion in the angles of this particular complex. It means agostic interaction arises due to the electron deficiency on the metal, and it pulls the electrons of the methyl groups. That is why this angle have been distorted. And for this particular reference, you can directly follow this review article for agostic interaction. This review article will lead you from the birth of the agostic interaction, how it was analyzed, how it was like discovered. Let's move to the next question. The elimination product of the following reaction of rhodium complex in the presence of carbonyl at 35 bars and 353 Kelvin temperature. The options are iodine, methyl iodine, and methyl carbonyl iodine and iodine complex. What may be the answer for this particular question? You have around 2 minutes to address this question, and then I will be addressing this. So, if we see, this is the Monsanto process, and it works from here. If we see here, methyl iodide comes in the cycle, and here the complex formation, it comes here, migration and the complex formation. Sorry. Yeah. Yeah. Complex formation. Okay. Then when carbonyl comes in the cycle and it is the reactant, and this remaining goes to the next cycle, and again regeneration of catalyst and cycle goes on. So here this complex comes and reacts with the water, and water is removed, acetic acid is formed. This is called the acetic acid formation via Monsanto process, and here we get this product which was our correct option. This is the elimination product. If we see here, elimination occurs here. This is the product. Okay, let us move to the next question. So among the below platinum complexes, which one is the most thermally stable? I have addressed this type of questions around 2 times during my previous 3 lectures. So I will be expecting an answer from you guys. Please tell me which is the correct answer. You have only 1 minute for this question. Among the below platinum complexes, which one is more thermally stable? Unstable, most thermally unstable. Among the below platinum complexes, which one is the most thermally unstable? This, or this? So if we see here, alpha, beta, alpha, beta, alpha, beta, alpha, beta, alpha and beta, alpha and beta here, alpha and beta, alpha and beta. So if we correctly see here, no beta hydrogen, no, here we have beta hydrogen, but it is arrested due to a ring formation. It cannot move. So this one also. If we see here, here we have beta hydrogen which can go elimination. And if we see here, if it goes to elimination, this is the most unstable. And here also, if we see no beta hydrogen, that's why it is also stable. So if we see, this is the reference given in the book B.D. Gupta. This is how this elimination occurs. That is why it is really thermally unstable. Let's move to the next question. What is the plausible structure of the intermediate involving in the following reaction? A or B? None of the above or both? This is A, this is B. So if we see here, this is how it will go. It is already a 18 electron system. If we want to insert PPS3, direct attack is not possible. That means first one elimination will occur, carbonyl will go outside, and then PPS3 or this ligand will come, and again 16 to 18 electron complex formation will happen. Okay, this is how this question will be addressed. Any doubts? So that means we need a vacant site. This both can be done. Both A and B are the answers for this question. Let's move to the next question. The compound that undergoes oxidative addition in the presence of H2. If we want to go to oxidative addition, we need some eligibility criteria which we have discussed. Let's implement them. Here total electron count 18 already, so it cannot go 18 to 20 for oxidative addition. So that means if it is going from 18 to 20, it will get unstable. That's why this particular complex will not go for the oxidative addition. Further, let's go to the next complex. 5, 6 and 6 plus 1, total 18, cannot undergo oxidation addition reaction again because it is already in a stable form, and if we go the electron count will be 20. Now iridium complex, if we see 9 for iridium, 1 for chlorine, 2 for carbonyl, and pph3 2, total 16 electron counts, and it can go for the oxidative addition reaction, and this is how it will go. Again, if we see this complex, 5, rhenium 1 and 7 for rhenium, hydrogen ke liye 1, around 13 electrons, 13 to 15 complex formation is not possible. So our correct answer is iridium complex. Let's move to the next question. Which of the following does not undergoes oxidative addition with methyl iodide? Again, it is asking for oxidative addition. We need not to see about this. Oxidative addition will occur only on the complex head with the reduced number of electrons. After 18, if compound is following 18 electron rule, it is not possible to do the oxidative addition reactions on them. Let's see. So again, if we see here, 16 electron oxidative addition can take place with this compound. If we see here, 16 electron on this also oxidative addition can take place. Here also oxidative addition can take place. So if we see here 16 electron, but titania is already minimum oxidation state, so it is not possible. So does not undergo where? Here. Let's move to the next question. I hope this uh, solution is clear to you guys. Which of the following case reductive elimination occurs in faster rates? So again, we have already discussed about reductive elimination rates, electron-rich ligands, electron-poor metal centers, bulky Nicel ligands, and all of the above. So if we see here, we are given that a high formal positive charge on metal, the presence of bulky groups on the metal, and an electronically stable organic compound. Okay, if we see these eligibility criteria are fulfilled by a complex, then it will undergo the reactive elimination in faster rates. Let's move to the next question. The typical electronic configuration of the transition metal center for oxidative addition. It is D8 and D10. Let me tell you how. For example, oxidative addition of iridium 1 to iridium 3 is common, but an oxidative addition from Fe3 to Fe5, while possible, is unlikely to occur. The tendency of the complexes to undergo oxidative addition is governed by the electron density on the metal center, that is, the ease with which metals can be oxidized. Such reactions are most common in the transition metal complexes, which are generally square planar with the D8 and D10 electronic configurations. This reference comes from B.D. Gupta book, so you can follow the book for this particular problem. Let's move to the next question. Here we will start with the assignment number 4 of year 2022, and this is the final assignment of year 2022, and also this is the final lecture of this session. So which one of the following is a Crabtree's catalyst? So for such type of questions, which one is Wilkinson catalyst and which one is that catalyst, which one is Monsanto's catalyst, you need to learn from books. As we read the books, we will understand that this particular catalyst is for this particular name. So if we see here, this is used in hydroformylation reactions generally. We see here this one is Wilkinson's catalyst. This is Shaw-Ostburn catalyst. We have discussed about this catalyst in our previous lectures of metal-mediated synthesis. And this is the Crabtree's catalyst. This is a homogeneous catalyst for hydrogenation and hydrogen transfer reactions. Let's move to the next question. In asymmetric hydrogenation, chiral aliphatic diamine can be used in place of phosphines because nitrogen is more electronegative, amines are poor coordinating in nature, inversion barrier for nitrogen is very low, nitrogen cannot be bind the substrate efficiently. This is a very interesting question, and I will expect you guys to answer this question. In asymmetric hydrogenation, chiral aliphatic diamine could not be used in place of phosphines. Why? For amines, we have a big story, and that we will discuss in this question. Do we have an answer for this question? Okay, let's see. So, if we see here, I haven't put any answer for this question. We will discuss here. If we see, this is our amine with the lone pair, right? So, what happens? It comes in plane. Again, if we see this type of inversion happens in amines. That is why the asymmetric synthesis or hydrogenation is very difficult in the presence of amines. That means inversion barrier of the nitrogen is very low, and in the case of phosphine it is very high. Phosphines do not do the inversion. That is why amines are generally not used for asymmetric hydrogenation. Let's move to the next question. Nylon industries use reaction catalyzed by to synthesize precursors of nylon 6,6. What may be the correct answer? Let us see. Hydrocyanation and nickel cord 2. See, this is COD, nickel. What happens in the presence of phosphine ligands? This formation occurs, and this is the activated adduct. This adduct gives us the formation of nylon 6,6 type of compounds. Let's move to the next question. Shock Osborne catalyst requires non-coordinating anions because these questions we have already discussed in our previous session of metal-mediated synthesis. We will again discuss it, but I will expect you guys to answer this question. Shock Osborne catalyst requires non-coordinating anions because to increase the solubility to make metal center electron deficient for a stronger binding of olefins to abstract proton from substrate, not necessary to have non-coordinating anions. Do we have an answer for this? Okay, let's move to the answer. So if we see here, to make a metal center electron deficient for the stronger binding of olefins. See, this is an example we are presenting here. Okay, let us move to the next question. Predict the product for the following reaction. See here, we have hydrogen, we have a metal in the positive state, and we have this substrate. So if we share where are the reactive centers, this can be a reactive center, this can be a reactive center. Now I have already almost given you the answer, and I will expect you to tell me the correct answer for this question. Hydrogen in the presence of metal. If it C is alkene, it will directly go for the hydrogenation of the alkene. So here hydrogenation of the alkene is happening. That means this and this are not our desired product. Here the hydrogenation is occurring in both of these two. So if we see here, due to the presence of this metal, it will directly come empty from this oxygen center. So tell me the stereochemistry of this product, either this stereochemistry or this. That means above of the plane or below of the plane. See, I have eliminated the options one by one. Now I am approaching to the answer. This should be the approach for gate and net type of the questions. So he's here, can understand. This is how this whole question is going on. Take it as a R group. So if we react it here, this is our metal complex and it will react with this alkene as I have told in the earlier. So if we see here, it will directly coordinate with the oxygen. So the answer will be, now we can tell the answer. The answer will be this. Because of its size, it will come from NT of this oxygen. So this methyl will go above of the plane. Let's move to the next question. Which one will be the major product? So if we see here, we have a cobalt complex, hydrogen and carbonyl, and we have already discussed in the previous question. I need to show you where here hydroformylation occurs with this catalyst. Let's go back to the question. I have already told you the answer. Let's see who is going to give me the correct answer. Here I have already given you the mechanism of this question. If you see here, directly hydroformylation is happening via reductive elimination pathway. So this is the correct answer. Let's move to the next question. Statement 1, major drawback of shock Osborne catalysis is the presence of sacrificial olefin dihydride hydrogenation. Catalyst cannot be used for synthesizing artificial amino acids. Both 1 and 2 are the false because it is not sacrificed, and also the dihydride hydrogenation catalyst can be used for the synthesizing artificial amino acids. We can see it here. See this. Okay, let's move to the next question. What is the final product of the following reaction? So see, we have here uranium chloride and there are two reactive centers. It will prefer to react with the alkene, and here is the mechanism. Firstly, the PPS3 removal and a vacancy is generated here. Here, hydrogen insertion. So here, the insertion is happening. Then the reaction with this. So if we see here, alkene is reacting with the metal center. Then migratory insertion, beta migratory insertion. Directly this comes here. And alkene is not in the picture. Now this complex is formed. So if we see here from this to this, five membered ring formation is occurring and the metal complex is released. So this is our product. This is our correct answer for this question. Let's move to the next question. Find the wrong statement. Wilkinson's catalyst is best for tri and tetra substituted olefins. In Manchester acetic cycle process, catalytic hydrogen iodide is used to make oxidative addition easier. Yeah, exactly. We have seen this in the reactive cycle. Asymmetric hydrogenation is possible by using chiral phosphine ligand. We have already discussed that amine ligands cannot be used, but phosphine ligands can be used for asymmetric hydrogenation. A crystallized intermediate from a reaction mixture may be off-cycle intermediate. This is also true. So if you see here, Wilkinson catalyst is not best for tri and tetra substituted olefins because uh, it is already bigger in size, and tetra and tri will introduce steric hindrance while using the Wilkinson catalyst. Let's move to the next question. Predict the appropriate agent for the following transformation. So we have already seen that. So if we see here, this iodine is directly being converted to carbonyl group, and here this alkene being reduced. So if we see here, we need carbonylation where it is happening here and here and here, and again the reduction of alkene group. This methanol can give the hydrogen, this also can give the hydrogen. So these two are our recommended sources, but we know formylation is occurs only with the cobalt, not with the titania. Let's see. So if we see here, this product is done with the cobalt only because it is a exclusive example of hydroformylation. So during this sessions, I should acknowledge Professor Devaratamaiti for giving me an opportunity to deliver the problem sessions. And also, I should acknowledge the support from my supervisors, Professor Pradeep Mamaji and Professor Kaushik Ghosh at IIT Roorkee. And I am thankful to my friends Kajul, Sakshi, Sumit, and Anuj for helping me out during these sessions. Thank you very much. And these sessions will be available on YouTube, as well as the presentations will be shared on the link. And if we have any queries, this can be discussed in the discussion forum. Thank you very much.